Welcome back. This is part 2 of our final video series. We're going to talk about complex numbers in polar form. This video is just going to be a couple examples going back and forth from polar to rectangular, rectangular to polar. And then in the next video we'll talk about why this is important and what we're doing it for. So I already have a complex number ready to go up here. It is -5 plus 5 root 3i. So I'm just going to get started converting this into polar form. If I need it to be in polar form, first we need an r, and as usual, r is the square root of a squared plus b squared, just a Pythagorean theorem kind of deal. So r is going to be, a squared will be 25, b squared will be 25 times 3 is 75, so r is the square root of 100, which is 10. Pretty straightforward there. I also need to find a theta if I'm going to transform this into a polar form complex number. And for that, we have that the tangent of theta equals b over a. In section 7.3, we would have said y over x, but we don't have y's and x's anymore. We have a's and b's. A plus bi. So, the tangent of theta equals 5 root 3 over -5, which is -√3. So from here, we have to be careful, just like always. If we take the arctangent of -√3, we're going to get -π/3. The arctangent will give us this angle down here, -π/3, which is not where we want to be. This is a quadrant 4 angle. This is a quadrant 2 point. So I got to be careful. If I want the quadrant 2 point, you could just add pi to this, or if you're in degrees, you could add 180 degrees. Or you could just kind of look at your unit circle and figure out what is the quadrant 2 angle that has the same arctangent. And it turns out that that angle is going to be 2π/3 or 120 degrees. So I have an r, I have a theta. I can just write this thing in polar form. The polar form version of this complex number is 10 times the quantity cosine 120 degrees plus I sine 120 degrees. And that's it, you're done. You got the radius, you got the theta, you got the format. That's all you need. All of the math is basically the same as what we were doing in section 7.3. We just attached some funny looking eyes to it. So, I want to do another one of these. Maybe this time I'll go backwards. I want to see what happens if I start with 3 times the cosine of -30 degrees plus I sine -30 degrees. This is the first time I've started with a polar form complex number, and as I am making this up, it occurs to me that I should mention some of you may be wondering, what do you do if these numbers are different? And the answer to that is, these numbers should never be different. If you're going to express a complex number in polar form, you only have one theta. The theta appears twice in this format because you need to put it in a cosine for your a value, and you need to put the same angle into a sine for your b value, but these should always be the same angle. You'll never really get a complex number with different angle values there. So, this is my complex number in polar form. If I want to convert this into rectangular form, you literally just have to simplify this expression. Like, you start by evaluating the cosine. The cosine of negative 30 is root 3 over 2. The sine of negative 30 degrees is negative 1/2. I've just realized that I have designs for this example, and I wish there to be fewer fractions involved. I'm going to change it just a tiny bit. Bear with me here. I want this to be a 6 instead of a 3, just so that some of these fractions cancel out. So we'll switch that around. No one even noticed. It's good. It's safe. It was a 6 the whole time. Trust me. Don't rewind the video. Trust me. And then once you've simplified your cosine and your sine, all you have to do is distribute this thing in here, and you should be left with 3 root 3 on the front end after 2 cancels from these guys, and a negative 3i on the back end after a 2 cancels from these guys. So both of these operations are things that you have done many, many times before. You take the sine and cosine of angles all the time. You have a unit circle, you can do that. You multiply numbers by 6 all the time. That's literally all there is to transforming a polar form complex number into a rectangular form complex number. You just evaluate the trig and then you distribute the radius. It's extremely straightforward. So I have this number as 3 root 3 minus 3i. That is my rectangular form of this polar form complex number. So that's one example going in the polar direction, one example going in the rectangular direction. Now we get to talk about why we're doing all of this. There has to be some payoff for writing numbers like this. This kind of looks like a mess. There has to be some good reason that we're doing this, and it's not to make you suffer. There are definitely some sections where the reason we do it is to make you suffer. It's a big conspiracy all math teachers are in on. But this one has practical use, and I'm going to talk about that now. The practical use is, I want us to think about what happens if I were to multiply these two numbers by one another. And we've done complex number multiplication before. That was a big part of section 1.4. It was kind of a pain because we have to do the FOIL thing from start to finish, and then after we do the FOIL thing, we have to simplify the I squared bits and try to figure out what's going on with all that. So here I'm going to do that process, and we'll see what happens. And then we're going to see what happens if we try to multiply them when they look like this. And you might be surprised how convenient this is going to get. First, I'm going to multiply these in rectangular form because that's what we're used to. The first terms of each should give me a negative 15 root 3 here. The middle terms should give me a 15i. Hold on. Yes, positive 15i. 15 times 3 should be 45. 45i there on the back end. And then the last term should give me a minus 15 root 3i squared. So again, negative 15 root 3 from the first term. The middle term should be positive 15i from these two, and 15 times 3i should give me 45i for the second middle term. These root 3's are getting messy, I know. Bear with me. And the last term, the I squared term, should be negative 15 root 3. So that's where all these pieces came from. Now I have to simplify it. This thing, we know, is going to turn into a positive 15 root 3. These things can be combined into 60i, and this is negative 15 root 3. Now we have some cancellation. 15 root 3s are going to go away. Convenient. The product of these two things is 60i. The real part is gone. If we write 60i in polar form, 60i is just straight up and down. So I kind of already know that the radius should be 60 and the angle should be 90 degrees. So I'm just going to actually write that. This is 60 times the cosine of 90 degrees is 0. The sine of 90 degrees is 1. So this is giving me my 60. 0 is the real part, 60 is the imaginary part. This is it. So this is me multiplying two numbers in complex form multiplying two complex numbers in rectangular form, simplifying it out to get a new complex number still in rectangular form, and then converting that into polar form. But I want to talk about multiplying these numbers in polar form. What we get at the end of everything is a 60 here, which seems pretty convenient. If I was going to multiply these two things, 60 is what I would want to happen. And the 90 that I get here is also pretty convenient. That's what happens if I just add these two angles. So here's the good news. Multiplying complex numbers in polar form is actually much easier than doing it in rectangular form. You don't have to do the FOIL thing, you don't have to do the I squared thing, you don't have to do the simplification thing. If you have two numbers in polar form, literally all you have to do is multiply the r's and add the angles. And that's it, and you're done. Multiply the r's together, get your new r, add these two angles together, get your new angle, you're finished. That's all there is to it. If you can multiply two numbers and add two other numbers, you can multiply numbers in complex form. It's super straightforward. It's so straightforward that it has a fancy name that I cannot pronounce. The name is French, and it's something approximately close to de Moivre's theorem. And maybe it's not close to that. Maybe that's a horrible butchering of the actual pronunciation, but that's the best I can do. De Moivre's theorem says if you put two numbers in polar form, you can multiply them by multiplying the r and adding the angles. I'm going to write that down in its general form and then cut this video and start a part 3 where we do some examples of this. The De Moivre's theorem, the fancy version of it looks like R1 cosine theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. So this is just two generic complex numbers in polar form. And the theorem says that this equals R1 times R2, so the product of the radiuses, times the cosine, theta 1 plus theta 2, plus I sine theta 1 plus theta 2. So, lots of fancy symbols going on, but what this really is saying is multiply the r's add the thetas. That's it. That's de Moivre's theorem. Multiply r's, add thetas. That's all you got to do. And that's the ease of this process is pretty much the entire reason that we put complex numbers in polar form at all. In part one of this video, or part one of this series, I mentioned that a lot of vocations will use a shorthand for this polar form, like r angle theta. I think it looks like this. R angle theta. I'm not an electrician or an electrical engineer, so I'm not entirely sure. This is just a guess. But I know that there's some shorthand that they use for writing these things. Complex numbers are very, very important for modeling the way that electricity behaves. And so a lot of times you have to multiply them because of Ohm's law, which I also forgot something about voltage and resistance and amps. One of those things is the product of the other two, I think. I don't know. Still, not an electrician. But complex numbers get invoked a lot in electricity, electrical engineering, and being able to multiply them together using de Moivre's theorem, where you just multiply these numbers and add these numbers, is much, much, much easier than having to do FOIL every time and then simplify the I squared term into a negative real term and then combine your like terms. This will save you an enormous amount of work ultimately if you can just put these in polar form and use de Moivre's theorem to combine them. So that's it for this video. Part 3 is going to involve a handful more examples of each of these things, and then that'll be it. We'll be done with videos. Exciting.